We've looked at differential equations. We know how to solve a differential equation using separation of variables, putting everything involving y on the same side as dy and everything involving x on the same side as dx. What we're going to focus on today is not so much how to solve the differential equations, but we're going to solve a couple of differential equations within the context of a mathematical model. We're going to focus on the concept of how our results fit in with the scenario and what the values within our equation relate to within the given situation. So let's dig in. We'll look at one of the most common sorts of differential equations, exponential growth. We've mentioned this briefly before. If we have a population which is increasing at a rate proportional to the population, we can use this standard format, dp by dt equals kp. Now have a look at this for a second and think about what the values mean. dp by dt is the rate at which the population increases. That's the number of additional people in the population, say, per unit time, maybe in a year. So for instance, Fiji's population is increasing at a rate of 6% per year, which means, well, if they had 100 people, they'll have 106 by the end of the year. Given that they might have, let's say, 10,000 people, then they're going to have 10,600 by the end of the year. That's what a 6% increase looks like. And in that case, k will be 0.06. The rate of increase is equal to 6% of the population. That's the number of additional people they will get each year. So k is the constant of proportionality. When we say two things are proportional, we'll have a constant in there, and it represents the growth rate or the proportional increase. If it's a 6% increase, then we'll have 6%. If we have a 26% increase, something like a credit card debt might grow at 26% per year, then each year, however much you owe, increases by 26% of what you owe. You borrow 1,000, you forget about it for a year. At the end of the year, you now owe 1,260. You forget about it for another year, you will owe an additional 26% of the entire 1,260. Similarly, you've got a population of bacteria. Perhaps in your petri dish, the number of bacteria grows by 26% every hour. Then the total number of bacteria will increase by 0.26 multiplied by the population at present every hour. As you can see, this sort of thing is going to produce exponential growth, because the bigger the population gets, the faster it grows, and the faster it gets, the more rapidly it gets big, and the bigger it is, the faster it grows. So let's dive in and try modeling a real-life situation with differential equations. Probably at the forefront of most people's minds is a situation that's crying out for a bit of mathematical analysis. The number of UK cases of COVID-19 increases at a rate proportional to the number of UK cases of COVID-19. Because the rate of increase is proportional to the number of people infected, it's a classic example of exponential growth. We've got data on this. There were 383 cases on the 10th of March and 3,983 10 days later on the 20th of March. So we're going to set up a differential equation and then solve it. As a result, we should be able to predict the number of cases on the 24th of March. I'm recording this on the evening of the 23rd, so we don't have the data yet. We'll be able to see by the time you come to look at this, that information should already be online. You'll be able to see how good our predictions were. We're also going to estimate from this model when the number of cases will reach 1 million. And then we're going to criticize the model. We're going to think about what might not work about it, what's going to be implausible, and the inherent dangers of making predictions in the future when you've been told all the way through your mathematical career never to extrapolate data. So let's start with the differential equation itself. The rate at which the number of cases grows, that's your differential term. That's going to be dp by dt. And the number of cases itself, that's p. K is the unknown constant of proportionality. And sometimes this information will only be available in the form of some additional facts. Like in this case, we have 383 cases on the 10th of March and 3,983 on the 20th. Those two bits of information will be sufficient to calculate the value of k, but also to calculate the value of the arbitrary constant that will appear when we integrate. You'll see how that happens as we go through. To start with though, we rearrange this using the separation of variables method. We integrate both sides, so on the left we have an integral with respect to p, and on the right we have an integral with respect to t. I've left the k on the right hand side so as not to complicate things on the left, The top is the derivative of the bottom, or more simply, it's just a 1 over x situation. So we get ln p on the left, and on the right, k is a constant, it integrates to kt. And this is where your plus c comes in. Very important that you don't forget about it. If the question finishes at this point and you forget your plus c, it's quite possible that you don't lose a mark for it. But these questions don't finish at this point, and if you leave out the plus c, you've messed up all of what happens next, because you won't be able to get an equation that fits the data. There is one thing you can do to make your life a bit nicer here. When we rearrange to turn ln p into p, we're doing e to the power of both sides. And if you're careful, you'll remember that you're doing e to the power of the entirety of kt plus c. Not the same as e to the kt plus e to the c, but it is the same as e to the kt multiplied by e to the c. And we're allowed to rewrite e to the c as capital A. C was an arbitrary constant we didn't know. A is a different arbitrary constant. It's e to the power of that original arbitrary constant. But we don't know it. We don't care what it is. We're going to calculate its value in a moment. But we might as well calculate the value of A rather than the value of C, because it makes no difference. As we'll see, A corresponds to the initial number of cases, because if t is 0, the e to the kt term cancels out. So let's define things in a way that makes life a bit easier. Instead of using t equals 10, let's say that t is the number of days since the 10th of March. That makes the 10th of March 0 days since the 10th of March, and the 20th 10 days. So we have information now about what p was when t equals 0. And by substituting that in, you can see that a comes out to be 383. If you think about this as an exponential graph, it's an exponential curve which, instead of crossing at 0, 1, like y equals e to the x, it crosses at 0, 383. In other words, at the very beginning, or when t equals 0, we already have 383 cases. The next bit of information we put in, we can now use the fact that we have the value of a. It's not the end of the world if you can't solve directly and find a from your first equation. What you'll end up with is two equations in a and k, so simultaneous equations, but you can deal with them by dividing one by the other, and that will allow you to cancel out a if you need to, find the value of k, substitute it back in. But in this case, we can divide through by 383, take logs and divide by 10, and when you've done all of those things, you'll end up with a value for k. When you substitute it back in, you'll have something that looks like not just the general solution, which is what we had over on the left hand side, p equals a to the kt, but now we've got what's called the particular solution. So we've taken the information that it was given to us, and we use that information not only to find the value of a, but also to find the value of k. We now have everything that we need to completely describe this situation. One other little thing you might notice, we can write this as e to the power of 0.234t, or you can separate it out as e to the 0.234 all to the power of t. And e to the 0.234 is 1.26. Now, I find that a more helpful way of writing it in this case. E to the power of something is much more useful if you want to do calculus with it. If you're going to differentiate it, which you could do here, you could differentiate this and check that what you end up with is dp by dt equals k times p. In other words, the same thing we got here. But if you just want to interpret it from an intuitive mathematical modeling point of view, 1.26 is more useful. Think about what happens as t increases. As we go from this day to the next day, from the 23rd of March to the 24th of March, t will increase by 1, and p will increase by a factor of 1.26. Currently it's 383 times 1.26 to the power of 13. We're 13 days past the 10th of March, and tomorrow it'll be 383 times 1.26 to the power of 14. In other words, the number of cases will increase by 26%. And in fact, we can use exactly that to deal with the next question. Predict the number of cases on the 24th of March. We can just substitute 24 into this. We could, if we already know how many cases there are today, multiply the number of cases today by 1.26, and that would do a similar thing for us. But we can get directly any given day just by substituting the number in. Remember, the 24th is t equals 14 because we've defined t to be the number of days since the 10th of March. I cannot stress enough how useful it is to make sure you have defined your terms. Sometimes P is not just the population, sometimes it's the population in millions. Sometimes it's the proportion of the population which is affected by something, and it'll be between 0 and 1, as we'll see later on. But if you don't define your terms, you won't know by the time you get to interpreting things exactly what your values mean. And in this case, T represents the number of days since the 10th of March. So if we want the 24th, we need T equals 14. So here's our estimate. You'll have to check in on Worldometer and see how accurately this represents the situation we're in. What I'm guessing you'll find is that the actual number of new cases, or the total number of cases, because that's what we're measuring, comes out slightly less than this. And you'll see why I think that when we look at the graph. I'm hoping that social distancing is doing what it should do. Based on your model, estimate when the number of cases will reach 1 million. Well, this is the same kind of question as before. The only difference is we know the value of P instead of the value of T. So we can substitute P equals 1 million. And although it may seem like a much, much bigger number than 9,700, multiplicatively, it's not that much bigger. What's happening multiplicatively is that numbers like 10 turn into 100 just as easily as 100 turns into 1,000, or as easily as 100 million turns into a billion. It took the human population millions of years, probably, to reach a population of 5 billion, and it's taken my lifetime so far to go from 5 billion to nearly 8 billion. It doesn't take very long to do the last few billion once you've already done most of the others. If you look on the Wikipedia page for world population, you'll see the first billion occurred many, many thousands of years after civilization started, after mathematics and literature began, and then the next billion happened somewhat quicker. And now we're doing so many billions that we're knocking them off every few years. There's some interesting things that we can say about this. When we criticize the model, one thing to notice is that this model is not just saying that we'll reach 1 million on the 13th of April, but this concept of increasing by multiplying by 1.26 means that we would reach 10 million after just another about 10 days. So from the 13th to the 23rd of April, we're suddenly at 10 million. And by the end of April, 100 million, which is already more than the entire population of the UK. So that's one of the things to be aware of. If this model really is accurate, it's not going to be accurate all the way up till the end of April. It can't be, because then more people would be infected than there are people in the UK. So we're going to max out at some point. And it's just common sense. When everybody's sick, no one else is going to get sick. The slightly crazy thing is, those last 20 days that I'm talking about, the last 20 days of April, that's when, according to this model, we go from 1 million to 100 million. In other words, 99% of the people who are sick at any given time get sick in the previous 3 weeks. So at the moment, nobody's sick. Nobody you know is sick. None of your friends are sick. You don't know anyone who knows anyone who's sick. And it will continue like that right up until a couple of weeks before practically everybody you know has been affected by it. This thing happens fast, and this is what exponential growth does. I'll link you to a useful video on that later. Not meaning to terrify you, just meaning to make sure you stay indoors. Criticize your model. Well, for a start, we can't extrapolate with confidence. Anytime extrapolation is involved, you have to be very cautious. It's important to notice that because this is what would happen if the disease went unchecked, countermeasures have been put in place. The aim, or the hope, is that we reduce that growth rate from 1.26 down to maybe 1.05, which would allow us to reduce the rate at which cases accumulate and allow people who get sick to get better in time for other people to get sick, and there'll be more hospital beds available, etc., etc. But there's another important aspect here, which is that the more people that are sick, the less chance there is, if you meet someone in the street and you're sick, well, if everyone you met was healthy, you would pass the infection on to some proportion of those healthy people. If almost everyone you meet is already sick, you're not going to pass it on to that many people. Most of the healthy people, they're not around anymore. All you're seeing is sick people. So there's a slightly different way of measuring that, which we'll get to in a moment. First of all, This is a graph I've knocked up from the data on Worldometer, and you can see what's happening in the last few days. Since some fairly stringent social distancing measures and closing schools has happened, the number of new cases has been lower than an exponential model would predict. In fact, by today, they were expecting approximately 7,000, or at least we would have been based on the data, but we were down at less than 6,000. So some of this is due to some natural variation, and some of it will be due to the fact that people are not necessarily being tested just because they might be ill. And there are all sorts of other factors to consider. We have to be very careful extrapolating just from the last 3 data points as well. But it's worth noticing how close these points are in general to an exponential curve. This model is not just good, it's incredibly good. It's really, really accurate. If you calculate the product moment correlation coefficient, which you can do if you code this data, take logs of the number of active cases, and you get this graph. This is a straight line graph, and you can see that although the points wobble a bit above and below, they pretty much follow that line. And yes, we've got a bit of a dip at the moment. It's quite possible that it'll go up again a little bit above the line, just like it has earlier on. But that graph shows us that an exponential model is a very, very good fit for this data, at least at this point. As we've already seen, extrapolating beyond this is a little bit risky, but there are other models that can help us deal with that. Now there's a few links I'd like to point you in the direction of. The first one is where I got the data from. Not only do they give you the graph that I've shown, but they also give you the log graph, and they show for a wider period. I was only showing you the last little while, but this shows you from the beginning of February, so you can get a clearer sense of what's happening. You can also look at other countries and see how things have played out. China, for instance, got fewer new cases today than we did. So they've gone past the point where the number of cases is increasing. They reached the peak. They're now on the way back down. They had a very stringent containment policy. You can look at what happened in Italy where they didn't, and compare the different graphs and the shapes of them with what we're seeing in the UK. Really helpful video that I found was this one here. Can't remember the name of the channel, but I've put links to this so you can go and hunt for it. It describes exponential growth in some really useful ways, and it talks about it with relation to the data, not just for the UK, but this is for all cases outside mainland China. And then if you've not come across 3 Blue 1 Brown, you really should check it out. This guy does animation along with his videos that is really cleverly put together to help make sense of some very high-level mathematical ideas. This one is absolutely accessible for people at this current level that we're at right now. Quite a lot of what he does goes above my head to some extent, but the videos are still worth watching because they give you an insight into the maths beyond as well as the maths that you're currently dealing with. He does a few little simulations, and he gives you some explanation of what goes on after the exponential bit of the graph stops. That's what I want to briefly talk about for the next part. So we have a slightly different model. It's called a logistic model, and the reason that I want to include it here is that it involves a mathematical technique that we've talked about a little bit before. It essentially takes into account the fact that people who are already infected cannot get infected again, and therefore the greater the proportion of the population that's infected, the less likely you are to infect somebody else. dp by dt is linked to both of these things, p and 1 minus p, and here p is the proportion of the population which is infected. So it starts out very low, as in close to 0, and it increases as time goes by up to 1. Now, one other thing to mention here is that t corresponds here to the number of days since the peak. So I'll show you what the graph looks like, but that basically means that the infection rate will be the greatest when p and 1 minus p are both 0.5 in this case. So we ramp up from t minus 20 days, minus 10 days to 0, and then 10 days, 20 days is when the infection rate is trailing off again. Let's look at what it breaks down into when we start solving this differential equation. as before, we can use separation of variables, and in a similar way to the exponential model, you'll find there aren't any t values in this. We still need to get everything involving p on the left, so we'll divide through by p times 1 minus p. We'll leave the dp where it is, we multiply by dt, and then we integrate both sides. So on the left we're integrating a fraction with respect to p, and on the right we're integrating a constant with respect to t. Well, the constant can be dealt with easily. The fraction breaks apart into partial fractions. If you look closely, you'll find that we have a p times 1 minus p. It's factorized already for us, so we can break it into something over p plus something over 1 minus p. And I haven't gone through the partial fractions steps, but I would encourage you to have a go at that. Make it a over p plus a over p plus b over 1 minus p, and then try adding them together, work out the values of a and b, check that it works. We can fairly quickly verify that this matches. If we look closely at the values, you can do 1 times 1 minus p plus 1 times p, and you should find we end up with a 1 on the top, so you can verify that that matches there. Now, if you want to integrate that, you can use the fact that 1 is the derivative of p, as we saw before with the exponential model, but also the 1 on the top of the second fraction is almost the derivative of 1 minus p. In fact, with an extra minus sign thrown in, that'll work. So we can think of it as 1 over p take away negative 1 over 1 minus p. That might be the nicest way to think about that one. You could also remember to divide by the derivative of 1 minus p, because it's just something linear. However you choose to do it, you should get negative in here, so ln p minus ln 1 minus p. And on the right hand side we still have kt plus c. We could do e to the power of both sides at this point and use index laws, or we could use log laws straight away and combine the two terms on the left. There's a bit of algebraic jumping through hoops from this step onwards, but it's worth doing because it is possible, even if it doesn't look like it, to get this in terms of to get p in terms of t. So we can make p the subject. First we'll do e to the power of both sides, and I've missed out a k in here, but p over 1 minus p equals e to the kt plus c, which will give, when you turn e to the c into a e to the kt. Now, if you flip that over, take the reciprocal of both sides, then we can break apart that fraction, 1 over p minus p over p. We can add the 1 to both sides and flip it over again, take the reciprocal. Looks a bit messy, but remember we can multiply any fraction by the same thing top and bottom. So if we multiply the entire fraction here on the top by ae to the kt and on the bottom by ae to the kt, then some things cancel out nicely and we end up with something a bit more elegant. P equals ae to the kt over 1 plus ae to the kt. What's interesting about this is there is exponential growth in there, the same exponential growth we saw before, but there's also exponential decay, because this term on the bottom is exponential growth, but it's on the bottom of a fraction, it's in the denominator. So as t increases, the numerator increases, but so does the denominator. And the denominator's got that 1 plus term. So if t is 0, then you just get a over 1 plus a. But if t gets very small, or a large negative, or if t gets large, a large positive, then it's going to tail off and approach specific limits. This is the shape the graph gives us. It's called a sigmoid curve. The blue one is the one you want to be looking at. Starts off small, it increases, and it looks a lot like an exponential increase at this point. That's what I've put next to it for comparison. The purple one's an exponential increase. It increases up to this point, and from that inflection point there, it starts to increase at a decreasing rate. So the gradient is always positive, but the concavity, the rate of change of the gradient, that's not always positive. The gradient is positive and increasing up to x equals 0 or t equals 0, and the gradient is positive but decreasing. In other words, it has a negative second derivative from t equals 0 onwards. You can see how this diverges from the exponential graph, and it does so relatively early on here. We can see as we get closer and closer to the inflection point, this becomes further and further away from the exponential model. And one of the things that we will be looking for as we do an analysis and as people are anxiously watching the data to figure out what happens, they're trying to predict when we might reach this inflection point. The sooner that happens, the more we can tell. Once we've reached that point, we are roughly halfway towards the point where everyone who's going to be infected will be infected. So we can get a sense of where we're at within the process once we reach this point. The way we can tell we're at that point is by considering the growth rate at each point. Exponential growth increases at an increasing rate, but by the time we reach this point, we have a 0-second derivative, and that's what people will be looking out for in the data. Just for comparison, this is our current data plot. You can see there's not a lot here to tell us very much about exactly where we are within that graph. But remember, as we go further and further along, we should find that the exponential model becomes less and less accurate, and the logistic model, the sigmoid curve as it's called, that we get here, you might remember that from graphs like a cumulative frequency diagram. That's going to become a more and more accurate fit for the data. And eventually we'll find that the total number of cases that we have had reaches its limit, it remains the same. So we will have had a certain number of cases and we won't get any more. This graph doesn't go down because it's the total number of cases we've had, so it doesn't drop when people recover. It remains the same. All right.